I'm going to discuss some general concepts regarding waves. In class we've been talking about electromagnetic waves, but what I will discuss here will pertain to any type of wave, whether it's an electromagnetic wave, sound wave, or water wave. So here I'm looking at the function y is equal to 2 cosine of 3x. We know that the cosine will vary between plus 1 and minus 1 as the argument of the cosine here, which in this case is 3x, varies. Now the function y then is going to vary between plus 2 and minus 2 because we're multiplying the cosine function by 2, and this 2 is referred to as the amplitude of our function, of our cosine function. The cosine is going to be 1 whenever the argument of the cosine, in this case 3x, is equal to an integer multiple of 2 pi radians. Okay, so when n is equal to 1, we're going to be on this peak right here. So in that case, 3x is going to be equal to 2 pi, or x is equal to 2 pi over 3. So this peak right here occurs at an x value of 2 pi over 3. This first trough is going to occur when the cosine function is minus 1, and that will occur when the argument 3x is equal to pi radians, or when x is pi over 3. The distance at which a wave repeats itself is called the wavelength. So for instance, from crest to crest here is a wavelength, and so for this particular wave, the wavelength is 2 pi over 3 meters. I now want to define the wave number for a wave, and the symbol we use is beta, and it is equal to 2 pi over the wavelength. Okay, for this particular wave we're looking at then, beta is equal to 2 pi over the wavelength. We just found that the wavelength for this wave is 2 pi over 3 meters. So the beta for this wave is 3 inverse meters. And in fact, we will see that the number in front of the x here will be the wave number for our wave. So let me rewrite our wave as y is equal to 2 cosine of 3x, which is 2 cosine of beta x, or 2 cosine of 2 pi over lambda times x. So looking at the argument of our cosine function, we see that whenever x changes by the amount of one wavelength, then the argument of the function will change by an amount 2 pi. Y equals 2 cosine of 3x represents this stationary pattern. Now let's look at how we can turn it into a propagating or traveling wave. So in other words, we want the cosine function to move with some velocity, and let's assume in the plus x direction, like this. So we'll see that what we have to do is replace x with x minus the velocity times time. Okay, so let's say we want the velocity to be 2 meters per second in the x direction. So for x, we're going to substitute x minus 2t. So our original function was y is equal to 2 cosine of 3x. So for the x, we're going to put in x minus 2t. And so y is equal to 2 cosine of 3x minus 6t is going to represent a wave propagating in the plus x direction with a velocity of 2 meters per second. So let's look back at our wave, and let's concentrate on this peak right here. So if the wave is propagating, it means this crest is moving. Okay, and so that crest occurs when the argument of our cosine function is 2 pi radians. So as time increases, in order for the argument of the cosine function to remain 2 pi, x must increase. So in other words, if time goes up, 6t is increasing, so in order for this argument to remain 2 pi, x must increase, and so the whole wave is moving to the right. So for the argument, when the argument 3x minus 6t is equal to 2 pi, then y is equal to 2 cosine of 2 pi, which is 2. Okay, so let's take this and take the derivative with respect to time, so you have 3 times dx dt minus the derivative of 6t, which is just 6, is equal to 0 because 2 pi is a constant. So dx dt is 6 over 3, or 2 meters per second, dx dt being the velocity of our wave, as we originally assumed. Now, we saw the significance of this constant multiplying x. That's the beta for our wave. Let's now look at what the significance of this number, this constant that is multiplying the time is. So let me rewrite our function for our traveling wave. Y is equal to 2 times the cosine of 3x minus 6t. And let's look at the behavior of that wave at one particular position, and to make it easy, let's pick that position to be at x is equal to 0. So in that case, y is going to be equal to 2 cosine of minus 6t, which is the same as 2 cosine of 6t. Okay, so when t is equal to 0, 6t is 0, cosine of 0 is 1, so our function y is just 2. When 6t is pi over 2, the cosine of pi over 2 is 0, so y is 0. When 6t is pi radians, the cosine of pi is minus 1, so y is minus 2. And when 6t is 2 pi, cosine of 2 pi is 1, so y is equal to 2 again. So our function is going to oscillate from 2 down to minus 2 and then back up to 2. So looking at x equal to 0 as our wave is propagating, at this point it has a value of 2. It's decreasing to 0, decreasing to minus 2, increasing to 0, increasing back to 2. And the time it takes it to oscillate from 2 to minus 2 and back is called the period of the wave. Okay, so looking back here, at t equals 0, at location x equals 0, y has a value of 2. It oscillates down to minus 2 and then back up to 2. And so the time it takes that to occur is when t is equal to 0 to the value of t when 6t is equal to 2 pi. So that would be 6 times the period is equal to 2 pi, or the period is equal to pi over 3 seconds for this wave. Okay, so that's the amount of time it takes it to perform one cycle. So pi over 3 seconds per cycle. The frequency of the wave is just 1 over the period, So that will be 3 over pi cycles per second. And cycles per second is often referred to as a hertz, but we'll more often think of it as 3 over pi seconds inverse is how we will write that. Now, it'll be much more convenient for us to work in radians per second instead of cycles per second. And the symbol for the frequency in radians per second is omega. So that's going to be equal to 2 pi times the frequency. So omega is in terms of radians per second. We have 2 pi radians per cycle. And the frequency, F, in terms of cycles per second, is how we get the frequency omega in radians per second. So for our particular example where the frequency is 3 pi hertz, the frequency in radians per second is going to be 2 pi times 3 over pi inverse seconds, or 6 inverse seconds, 6 radians per second. So if we look back at this particular example where y is equal to 2 cosine of 3x minus 6t, we see that this number multiplying the time is the frequency in radians per second. So we could make the identification with the 3 being beta and the 6 being omega, and write a more general form for our wave function as y is equal to 2 cosine of beta x minus omega t. Okay, so for this arbitrary wave then with some beta wave number and omega frequency that's propagating like this, let's pick one of these crests here. Okay, let's say this crest occurs when the argument of our cosine function is equal to 2 pi radians, so that as time increases, x has to increase so that beta x minus omega t remain equal to 2 pi radians. Okay, so when that occurs, y remains 1 or 2 because the cosine function retains a value of 1, so you're riding on the crest of a wave. So again, let's take the derivative with respect to time of this equation here. So we'll have beta times dx dt minus omega is equal to 0 since the right-hand side is a constant. So if you solve for dx dt, you find that's omega over beta, which is just velocity. Dx dt is velocity, the velocity of our wave. And if we write omega in terms of our frequency f, we have 2 pi f over, writing beta in terms of 2 pi over lambda, we get another form for the velocity of the wave as the frequency times the wavelength. So both these expressions are useful, that the velocity is omega over beta, or the velocity is equal to the frequency times the wavelength of our wave. Now, if you wanted to write an expression for a wave like this, but one that's propagating in the minus x direction, then all you have to do is change this minus to a plus. Okay, and the way to think of that is, let's say you're riding on a crest of the wave, and so at the crest this argument is equal to 2 pi. So if time is increasing, in order for this to stay equal to 2 pi, x must be decreasing.